Hello everyone. I'm going to make a few more um, videos here for additional questions that came up on the practice exam. So we're going to start with 7. There were some requests for more time spent on this one, so we'll start with that. So how much heat is necessary? And when we see the word heat, that is telling us we need the heat equation. So I'm going to go ahead and write down the heat equation. So anytime you see the word heat, go ahead and imagine you'll probably be using this particular equation. Um, so how much heat is necessary to raise a 42.83 gram sample of copper? So we'll say mass is equal to 42.83 grams, and this is for copper. From 21 degrees to 115 degrees Celsius. So our initial temperature is 21 degrees Celsius, and our final is 115 degrees Celsius. And the specific heat of copper is given there. So specific heat is equal to 0.385 joules per gram degrees Celsius. Okay, so let's go ahead and try to solve this problem. When we have a heat equation, we will often want to start with figuring out what is our delta T. And we have our final, so delta T is equal to T final minus T initial. So that is what we will pretty much always have for delta T. If we do the math there, we get 94 degrees Celsius. And then we take that and we put that into the equation along with these other numbers. So the mass is 42.83 grams. The specific heat is 0.385 joules, and that's divided by grams and degrees Celsius. And then delta T is 94 degrees Celsius. One thing I do want to mention about the heat equation, we are still pretty much letting the units define how this works the way we do with all of the math in this class. The difference here is that with this particular measurement with the specific heat, we have 3 units instead of just 2. We normally have 2. Here we have 3. The units should still be canceling out. We're just not writing it as an equality the way we normally do because we can kind of see how these units work out. So the grams will cancel, the Celsius will cancel, and the units we have left are joules. So we have 42.83 times 0.385 times 94. If we do the math there, we get 1550 joules. That is the correct answer. We often want to report this with units of kilojoules. So if you did convert that to kilojoules, it would be 1.55 kilojoules. It does not ask for that though, so you could leave it as just joules. Okay, the next question I wanted to look at was there was a question about the one directly below here, specifically for the argon. So let's go ahead and look at that. So it says complete the following table, assume a neutral atom unless indicated otherwise. So this kind of table I believe you had on a previous worksheet and you had on a quiz. And you're given the symbol of the element and you're given this number is the mass number. So we can, when we see that 40, we can immediately write that down as the mass number. And then when we see the symbol AR, we can look at the periodic table. I'm going to go ahead and go back to our periodic table. This is the same one we used on the previous video. And we look for argon. We find argon is right here. And we see that number right there is the atomic number. So we write that number, we write 18 as the atomic number. You might also notice, let me go back to this, there's another number. The only number is the atomic number that we care about in this question. The number down here is the atomic mass. That is not the same as the mass number. The mass number is always a whole number. It is the number of protons plus the number of neutrons, so it has to be a whole number. It is actually given to us in the question, so argon 40, so that's how we know what that is. The number of protons is always exactly the same as the atomic number. The number of electrons is the same as the number of protons, unless we have a reason to think otherwise. It says assume a neutral atom, so if it's a neutral atom, these are the same. The only time we would ever have those be different is if there's information given that you have to end up with an ion. For this question, we don't end up with an ion. And then finally, we have the number of neutrons. The number of neutrons plus the number of protons has to add up to the atomic number. So we can do some quick math here. So 40 minus 18 will give us 22. So 22 and 18 add up to 40. That is then our number of neutrons. Okay, so that is our second question I wanted to look at. There are two more. So I had a question related to nomenclature. So I want to look at number 11 on the practice exam as a good example of a nomenclature type question where you are coming up with the name if you are provided with the formula. So let's look at that. One big clue in the practice exam is it specifically says these are ionic compounds. So you don't have to, in this question, you don't have to think about is it ionic or is it molecular. In this case, they are all ionic. However, if you were not given that information, what you would do is you would look at the periodic table and from the periodic table decide. So let's go ahead and look at a periodic table. So we have calcium and chlorine. So calcium is here, chlorine is here, metal and non-metal. So the name of that, so the calcium is in group 2. Group 2 is always going to have a +2 charge. So the name of this is just calcium chloride. Okay. We don't have anything in the name about the subscript 2 because it's an ionic compound and because calcium is always a +2. It is not a variable charge metal, so it has to have a +2 charge. So we don't say anything about the 2 in the name. In the next one, we have K2SO4. We have more than 2 elements. Anytime you have more than 2 elements, you're going to have a polyatomic ion. So we look at where is that going to be? Is it going to be the start or the end? It's usually going to be the end part. So we have SO4. So you also are provided with some common polyatomic ions. So anytime you think you might have a polyatomic ion, look on this chart and look for whatever that might be. So we have SO4. We see it's right there, and that is called sulfate. Okay, so then the K we find is right here. That's potassium. So the name of this is just potassium sulfate. Okay, so the key again is that you're finding sulfate on the list of polyatomic ions. Again, ionic compound, so we don't say anything about the 2. Last one, we have FeNO3 and parentheses 2. So first of all, Fe we find is right here. This is a variable charge metal. It's in the transition metal region. We don't know what the charge is. What that means is that we will have Roman numerals. Okay, whatever the charge is, we'll have a Roman numeral for it. So that's one complication for this question. The other one is that we again have a polyatomic ion. So we look on our list and we're looking for NO3. We find NO3 right here, and that is nitrate. NO3 had a -1 charge. You're given the charge here. So let's come back here. We have -1, -1. We have 2 nitrates. That 2 is telling us we have 2 nitrates. Because we have a -1 charge, 2 nitrates, that means we have a +2 charge for the iron. So the name of this is iron, Roman numeral 2, nitrate. Okay, there was also a question about number 14. What is the molecular formula of a compound found to have a molar mass of 60.05 grams per mole with an empirical formula of CH2O? Show all your work. Okay, so first of all, what is a molecular formula? What is an empirical formula? The empirical formula is the lowest, basically the lowest common denominator of all of the things making up the molecule. CH2O, we can't make that any simpler, say by dividing by 2 or 3 or 4. That's the simplest possible formula for that. So the first thing we need to do is find the molar mass of this, this empirical formula. So we have carbon is 12.01. Again, these are from the periodic table, so you can look these up. We have 2 hydrogens, 1.01. We have oxygen is 16. We add those up. So what? 16 plus that, so that's 18.02 plus that would be 30.03 grams per mole. This is called the empirical formula mass, which is simply the empirical formula, or the molar mass of the empirical formula. So then what we do is we take the molar mass of the whole molecule, and we take that and we divide that by the empirical formula mass. And this is going to be about 2. Actually, let me go ahead and do the specific, do the total math for that. So we have 60.05 divided by 30.03. So yeah, it's basically 2. You've got 1. I think 9996666. So that's going to be that. You're going to round that up to 2. I mean, you can look at that and see that as 2. Sometimes you might have to write it out first before you see that. So this 2 is telling us that we have for this mass for the molecule is twice the empirical formula. So what we do is we say 2 times CH2O, and we write that as C2. So 2 times the 1, 2 times the 2 is 4, so H4, and then 2 times the 1 is 2. So C2H4O2 would be the molecular formula. And what that is telling us is that in a molecule of this compound, you have 2 carbons, 4 hydrogens, and 2 oxygens in a molecule. That's not the empirical formula. The empirical formula is the smallest whole number ratio. So you would look at this, divide by 2 to get back to this number. But we're looking for the molecular formula. So that's how we would do that. That is all the questions that I got as of Tuesday afternoon. If there are more questions, I might be able to answer them. More than likely, it will not be as a video, but as a just simply a response on Canvas. But if I am able to get some time on Wednesday, I might be able to answer those as well.